All right, so let's get started. Okay, first thing I'm going to do is I'm going to hand this out. I'm going to pass this around. Sorry. What you're looking at is something called Bus Pirate. You're like, "Arr, Bus Pirate." And it has to do with serial buses. So it is there to pirate, in the best sense of the word, serial buses. It's about $50. It's an open source project. It has a PIC microcontroller at the center of it. You can reprogram it if you want. And we're going to be talking about serial communication today. And that Bus Pirate right there is the least expensive, most accessible, not the most user-friendly, but at least expensive, student-friendly, from that perspective, device for capturing and debugging serial interfaces on anything, basically. Okay, but while that's going around, I think I saw a question. Yeah?
Question. So we have the final project due April 5th.
Yep.
And the midterm is going to be 2 days before that.
Okay.
Is it possible if we can just push the final project due?
Could we push the final project due date to like Friday? So I'm not allowed to push any assessment past the end of semester. So Friday is officially the last day of the semester. Okay, I can push it to Friday. Yeah. Unless you want it like a Monday or something, like this Monday. No, but I'm totally fine with pushing it to Friday. Totally fine. Next question. Yeah, Brian.
For the midterm,
yeah.
If you want us to program something using like the ADC, for example, will
yes.
we provide the sensors, or do we have to bring our own?
Okay, so I understand that the whole midterm issue was a little bit of a surprise for a lot of people. So let me put it this way. The idea is to give you without making it a group project, more of an extended flipped classroom kind of experience. Okay, so the questions that you saw, the sample questions that I showed you, those are the kind of questions I'll ask. Okay, variations of those.
Sure.
And in terms of an ADC question, I could make it really complicated, but I'm not going to. The easiest, most straightforward ADC question, and it will be variations of this. I guarantee it. Okay, as all of you as my witness. I will give you 2 arbitrary resistors.
Okay.
I will tell you, I'll mark them ahead of time for myself, okay? I'll give you 2 resistors. Say a 4.7 kilo ohm resistor and a 1 kilo ohm resistor.
Okay.
And I'll say, arrange it as a voltage divider. I won't even tell you what the value is. I'll know what the value is for those resistors, okay? Arrange it as a voltage divider and tell me what the voltage is between the 2 resistors.
Okay.
By converting it in your software using your ADC at whatever configuration you want to set up on your Kinetis board.
Okay.
Just a second, preset. Hold on. There's no catch. Do you understand what I'm asking for?
Yes.
Does it sound like a trick?
No, it's not a trick. I'm just trying to process what you were saying.
What I'm trying to do is I'm trying to get at what's at the heart of an analog to digital converter. Do you understand what's going on with an ADC? If you get some value that comes out of it, can you convert that into an actual meaningful voltage? Can you tell me what the voltage was?
Okay. Side question. So the voltage that goes into the ADC, and when you display it, is that the voltage in millivolts?
The voltage, the value that appears in the ADC register has a unit called counts or quanta.
Yes.
It's meaningless, other than it's just a count value. But you know what the conversion factor is here. So I've gone over this with a few people before. I don't want to spend too much time dwelling on this because I actually want to get into the serial communication side of things, okay? But hopefully, this will make sense to everybody. Okay. R1 and R2. This is a voltage divider. Top of it's 3.3 volts because that's the reference for the high end of the ADC. Bottom end is ground. Okay? We're tapping off the middle because it's the voltage divider. If this is 500 ohms and that's 500 ohms, what's the voltage at the ADC? 1.65 volts. Okay? What does the ADC see? It doesn't see voltage. It sees this. If we have a 12-bit configuration for our ADC, this is what we see. 0 and 2 to the 12th. Yeah? Which is, sorry? 4,000, it's actually 4,096 minus 1. Okay? Because there's 4,096 steps, including the very first one, okay? So it's 4,095. That's why some of you have been reading your ADC and all you get is 4,096 or 95, and that's all you get, and it's really frustrating. It's because it's topping out at 3.3 volts, okay? Now, if I'm feeding 1.65 volts into it, what is my ADC reading? If everything's configured right. 2,000. 47 or 48, depending on what side of the fraction you're on. That's it. And then everything else is proportional. Your voltage goes up a little bit, then it'll be here. It goes down a little bit, it'll be there. So with the ADC code, you're going to get this value that comes out, okay? And you should be able to map that to that, and that to that. You should be able to do this. It's a conversion factor from volts to counts, or volts to quanta, depending on when you want to call it. Okay? Simon?
Is the voltage and the the quanta number, are those in a linear relationship? Yeah.
Yes, they are. There's a linear relationship between them. You can assume it's linear. You should always confirm that it is, okay? But you can assume that it is. How?
Yeah.
Because the engineers that designed the ADC on this system knew that most of you, as customers for their chip, would want it to be linear. So they created a linear system. It's almost always linear. Yeah.
Does it always top out at 2.3 volts?
On this board, it does. On the 9S12s that we were using before, they topped out at 5 volts.
Okay.
However, you can cut the connection to 3.3 volts and you can make it something else. It's the VREF L and VREF H. So voltage reference high and voltage reference low values. And if you look in the data sheets, you'll see references to those things. And you can modify it. So typically, we're not going above that range. Often we'll bring it down. Because often you'll have a really small signal and you'll want the voltage, the high voltage reference to be lower so that you can concentrate all your resolution to a little band. Okay? So you can get more meaning out of the small voltages. So often we'll drop it down. But there's a pin. There's a pin that you can feed an external voltage reference to. Yeah. There's an internal reference, high precision reference. There's an internal one. But you can also bring in an external one. Yeah. So if you're doing load cells or strain gauges or things like that, you'll often bring in a very stable, relatively expensive external voltage source and tap it in and feed off of it. So next year for your Eng 4000 project, if you've got some weird 5 volt or some other voltage source that is analog and you need something more than 3.3 volts, you can use a different voltage reference. And most microcontrollers support that. Yeah, but by default it's 3.3 volts. Okay? Other questions? Yeah.
You mentioned resistors as one of the things we're supposed to bring.
So those are the resistors for driving the current limit on the 7-segment displays. So anybody who's coming to write that test next week should be coming with the board like this, already wired up with the 7-segment display on it. Do it ahead of time.
And the resistors.
And the resistors. So you can test it out ahead of time, get together as a group, put all of them together, test them out, and bring it pre-wired. Okay?
How much are these resistors? Like what
Their ratings, I can't remember. There's something in the neighborhood of 300 or 400 or 500 ohms. Yeah. So somewhere in that neighborhood.
So it doesn't really matter then, right? The resistance.
Well, the higher the resistance, the less bright the LED will be. But in the sort of the multi-hundred range, you'll see it without burning out anything. Okay? But yeah, wire it up ahead of time, bring it. Okay, and then we can make it flash as part of the demonstration. Yes?
We have to bring our own resistors then?
Well,
There's nowhere to get them?
sorry. So in the lab kit documentation,
Yeah.
the resistors were listed in there.
There was 4. I thought we needed 7 for the LEDs.
Were there 4?
Yeah.
Okay. How many of you are missing resistors? Okay. For all of you who are missing resistors, I will go and get you some resistors over the weekend, and I'll have them available on Monday. Okay? So if by the end of the weekend you don't have the resistors you need, I will have them available for you. Come to see me during Monday office hours, and I'll give you the resistors. I'll go to Creatron myself and buy a bunch.
Does sales sell strips of them?
Does which?
Sale sells strips of them?
They sell bags.
Okay.
Typically bags, yeah. They do. So what I do, and I really like, and you may want to consider this as well, is I go and get these booklets of resistors that are pre-labeled from Creatron. Sale might also sell them. They're originally made by SparkFun. They're wonderful. Compact, they're glued together, you pull them out, they're labeled. It's like for next year for your projects and that, these are wonderful. Anyways, I'll get some more. I'll give them to you on Monday. Brian.
So we just need the resistors for the 7-segment display.
Correct. And I will supply the other resistors, the one for the ADC voltage divider.
Okay.
Yeah. Other questions? Okay. So the thing that's going around right now, how many of you have wanted to hook up Bluetooth or a GPS or some fancy peripheral device to your microcontroller and you didn't know how to do it? Yeah? Okay. So for those devices, if you wanted to hook up a GPS or a radio or something else, typically what you need to have is a serial communication capability, because what will happen is there'll be 2 to 4 wires, depending, maybe a little bit more, maybe a little bit less, depending on what protocol you're using, that will connect your little KL46 or your Arduino or whatever. And or say you wanted to connect your KL46 to an Arduino or your KL46 to a Raspberry Pi. You want to make an Internet of Things thing. In all of those cases, you can take some wires that allow a connection to occur between them that requires few wires, but allows messages to be passed back and forth. That's effectively what serial communications is. How many of you guys and gals use USB? For your phones, for a mouse, right? That's a serial device. There's 4 wires in it. There's a differential pair that allow differential signaling of the signals between the computer and the mouse. And then there's 5 volts and ground. That's a serial device. And your KL46 can actually behave, one of the USB ports on it allows it to behave like a mouse or like something else. It gets recognized. It can be recognized as a human interface device by Windows or Mac OS, etc. Okay? But in all those cases, unlike the 7-segment display that required like gobs of wires, if you were to get the same 7-segment display, but it has a serial interface to it, instead of, I can't remember how many wires I added onto this, lots, you'd only need 3 or 4 wires. But it requires a chip at the other end to decode the signals that are going through. So today what we're going to do is we're going to talk about, thanks. Thank you. We're going to talk about the serial communication aspect of things. And the KL46, just like most microcontrollers, has multiple serial communication capabilities. Some of them are wired in, and other ones can be programmed from scratch, like on an FPGA. There's something called Flex I/O that allows flexible I/O to be reprogrammed, not exactly like an FPGA, but similarly, it is flexible in nature and can be repurposed and retasked, okay? So there's some references here. We're looking at chapter 12 out of the Katie textbook. It's chapters 35 through 38 in that 1,000-page reference manual, which again, for the test on Tuesday, will be given to you. We'll have a paper copy available, okay, with just the chapters that are needed. And I've posted that on Moodle, so you know exactly what will be given to you, okay? All right, and these are actual slides from the ARM website, okay? So we can talk about, let me just display this. There we go, okay. Okay, so in the system that we have something called a UART, a Universal Asynchronous Receiver and Transmitter. We have SPI and I2C. And there's a couple of other protocols that are available. If you're in the automotive sector, then you'll see things called LIN and CAN bus. Those are other serial protocols. Your car, if you have a car or you've used a car, probably has a CAN bus network inside. CAN bus is effectively a serial port network. But the most common protocol or most common interface is this UART. It's been in computers since the early 80s, and it's basically on every single microcontroller with almost no exceptions out there. So if you're looking for a standard, easy-to-use interface that allows you to talk to your PC to decode what's going on your system, UART is the way to go. If you have special sensors or motors or other things like that, how many of you are using a digital temperature sensor, for instance? Some of those digital temperature sensors will either speak SPI, or I2C, I2C. Sometimes they have a different protocol, but those are the two most common digital kind of protocols. How many of you have memory cards on your phone? Those little sort of, not the SIM card, but the other card, you know, the one you can put your MP3s and stuff on. Your SD card, yeah. That speaks SPI. Okay, so internally, it has an SPI interface. And so if you wanted to add extra memory, or you wanted some way of data logging on your microcontroller and then take the card off and load it into your phone, for instance, and that's what a lot of people for in-field data logging will do. They'll have some remote sensor somewhere, and you send a technician up with their phone. They take the not the SIM card, the SD card out, they plug it into their phone, and they can read whatever that data had been logged in, okay? And so SD cards are a very common SPI interface device. Okay, why do we communicate serially? The real reason is because of cost. And it's because over time, the chips have gotten from big to medium-sized. So this would have been a chip back in the 80s. Then the chip in the 90s and early 2000s was about that size. Now they've gotten down to sort of, well, this isn't actually, from my screen, it's not even 2 millimeters. How many of you play golf? When you're rich and famous, you'll probably play golf, okay? But you've all seen golf balls, right? They got little holes in them. Okay, the smallest Kinetis ARM chip, so the one that you've got, the smallest one that they sell right now is 2 millimeters by 2 millimeters. It fits inside of the hole on a golf ball. okay? The pins on it are so small that the board has to be laser cut in order to make it actually fit on. It's like crazy, okay? They've gotten so small, these chips, that they don't have enough pins for doing more complex parallel interfacing to devices. So across the board, in just about every sector where they're using microcontrollers, they're going to low pin count, low wire count, serial interfaces to connect things together. So it's really important for you, if you want to be ready for the job market, to know how to use some of these serial peripheral interfaces. And so next year when you're doing Eng 4000, do consider using at least one of these serial interfaces to get practice over that 8-month period that you're developing your project, okay? So basically things have gotten smaller. The only interfaces that make sense anymore really are the serial ones. Okay, if you have the need for GPS, Bluetooth, USB, any kind of networking, complex LCDs, accelerometers, you name it, you're going to want to use some serial interface. Okay, so this is one of the key things that you want to know about for microcontrollers. All right. In the past, communications were based on a parallel method that for memory and things like that, and you used to actually find all the pins that were available for addressing and data busing and things like that on the microcontrollers. That no longer is the case, and so basically you never see this anymore on the outside of microcontrollers. Almost never happens. You will sometimes see it if you need to interface very large, very fast memory. So on the higher end ARM processors, where you need to, like it's basically a computer, like on a tablet or something, there you'll see where you have like gigabytes and gigabytes of memory, you'll see the parallel interfaces again. But on the stuff that you're all dealing with, it's all serial. So when you're doing serial transmission, you're doing one of two things. You're either synchronously transmitting and receiving, or you're asynchronously transmitting and receiving. And the difference between the two is the synchronization. How do you synchronize? With a clock. Okay? So if you don't have a clock, if your cabling doesn't allow for a clock, then it's asynchronous. It has no synchronicity. Okay? If it does have a clock, then you know it is a synchronous system. So the UARTs that we're dealing with, so if you've got a serial connection between a Raspberry Pi, for instance, and this microcontroller, there'll be asynchronous, no clock between the two. Okay, Brian?
So do both devices have to have a clock?
Yes. So unless you have a very special non-clocked microcontroller FPGA something, and that basically doesn't really exist very much, in all cases, they will have their own clock system that are independent from one another. So you could have your Kinetis board running at 48 megahertz, and you could have an old x86, 386 or something running at like 4 megahertz or something. And it would be totally fine. Because what ends up happening is you coordinate, you agree at what rate the data will transfer, and then the devices will lock in on the frequency that things are traveling in at, or they'll oversample in order to be able to compensate for any mistakes. Okay?
It's like the B9 file break.
I'm sorry?
Like in the old connection, the B9 does it file break when connected.
Okay, right. So back in the day, so asynchronous connections, if you had on the back of your computer, it looks like you all know what a VGA connector looks like? Yeah. VGA connectors have 15 pins on them, okay? This looks almost like a VGA connector. It has 9 pins, 1, 2, 3, 4, 5 on the top, and then 4 on the bottom. It's called a DB9 connector, and it generally speaks a protocol called RS-232. Okay, that's the type of transmission characteristic that it has. And so if you see one of these 9-pin connectors anywhere, in fact, on the back of that oscilloscope right there is one. It is a de facto standard. If a microcontroller has any serial port at all, it will be that one. Okay, it'll be UART to RS-232 or UART all by itself that allows an RS-232 converter to be connected to it. So what you were saying, okay, was that sometimes there's a pin or some other method for allowing one device to talk to the other device and say, I'm going to speak at a particular rate. And that rate would be something like 300 baud or 9600 baud, which is what fax machines often speak at. Yeah, there's a number of, there's very standard rates, okay? And the rate that this, so this little bus pirate can be sped up and slowed down to different rates, and you tell it, I want to speak at 115 kilobauds, okay? And it will speak at that rate, and it will listen for devices at that particular rate. And if you don't know what the rate is, you start at 1, and then the data will come in, it'll look like garbage, and then you increase and you increase and you increase until all of a sudden the signal looks good. The letters that are coming through look correct. But basically what it is, it's the speed at which data is being sent roughly in bits per second. So 300 baud is approximately the rate at which you can read on a page. So if the words were being displayed on the screen and scrolling on the screen, 300 bauds is sort of human readable rates. 2400 baud is barely readable. 9600 baud you can't anymore, and then everything after that, only a machine can read it. Okay? Just to give you a context or a perspective for speeds that we're talking about. Okay, any questions, concerns, or comments? Yeah.
So for synchronous communication
I'll go back. Yeah.
For synchronous communication, there's synchronization bits, right? Is that basically what?
So what'll happen is typically there'll be multiple wires. One wire will be like a transmission wire. One wire will be a reception wire. And then there'll be another wire that just goes up and down, up and down, up and down, up and down. And that's the clock signal. And typically in those cases, what you're dealing with is what's referred to as a master device, like a master microcontroller or a master PC or a master device like that, the main thing. And then all the other things are the peripheral or slave devices. So the printer is the slave to your PC. Your Bluetooth headset, although this isn't quite right, the Bluetooth headset that you wear is the slave to your cell phone. Your cell phone can be the master to all these devices, but if you hook it up to your PC, it might be the slave to your PC. So it's a relationship, and you define who's in control when. And so typically it's the master that sets the clock rate. And then what will happen is that the slave devices will synchronize to the rate of the master. Okay? To the point where in SPI, you have a signal called master out, slave in. So it goes out from the master into the slave, and then it has a master in, slave out. Meso and Mosey. Okay? Sound okay? Whereas if you have other, typically the asynchronous protocols, it's often two peers talking to each other. Two cell phones talking to each other. Two PCs talking to each other. Two base stations talking to each other. Sometimes they're slaves, sometimes they're masters, but they're basically treated as equivalents. All good? All right. So basically, the difference between them is one is synchronized, the other one isn't. When it's synchronized, it's typically master-slave. When it's asynchronous, often they're two peers that are equivalent in sort of the hierarchy. We'll get past, well, we're not going to talk about duplex and whatever. Basically, just think of the fact that typically there's a bunch of wires, they synchronize, etc. Okay, so when you have asynchronous serial communication, this is where we talk about UARTs. And an example that you might run into would be something like, how many of you know what a Raspberry Pi is? Not the thing you eat, although I'm really hungry and, you know. Okay, so you got a Raspberry Pi. Whoops. Like that. And then you've got your freedom board. You can get the two devices to talk to each other with a TX line, transmit, a receive line, RX, and a ground. With 3 wires, you can get the two to talk to each other, and they can talk to each other as equals. Okay? So next year, if you're doing a project that connects to the internet, for instance, it would be crazy for you to take that Kinetis board and connect it to the internet directly. All the software you'd have to write, all the interfacing, forget it. There's no point. You would go and get a Raspberry Pi or some other equivalent Linux device that can talk to the internet, but you can do all the really fast sensor processing and all the other good stuff that the Kinetis is really good at, that the Raspberry Pi is really poor at, and you transfer information over UART, over the TX and RX pins. And you can transfer really fast between them. Okay? Questions, concerns, comments? Yeah.
Isn't there like a Wi-Fi module or a Bluetooth module that you can connect to the Kinetis board that allows talking to your computer and the Kinetis board?
Okay, so if you wanted to say, for instance, to talk Bluetooth or some other complicated Wi-Fi, Bluetooth, etc., again, super crazy to go and create all the software that's required to talk Bluetooth or to talk Wi-Fi. Don't do it, okay? There are manufacturers in China that have come up with little chips that speak that protocol for you, okay? And it's a good thing because they're cheap, they're debugged, they're good. And you can implement them really easily. And what they do is they implement a UART to UART connection. So, for instance, I'll switch over here. So it's Bluetooth, right, that you like? Okay, so you got your Bluetooth right here. And it's a radio. And you got your, I don't know, your cell phone, right? Your cell phone speaks Bluetooth, right? Yeah? And it has a Bluetooth module on it. I wouldn't want for the life of me to write the Bluetooth software stack. Okay, I wouldn't even know where to start. But there's this little chip in here that knows it. And it also has a UART. And your Freedom board also has a low power UART that we'll talk about today. And you can connect TX, RX, ground, like that. And then you can send letters and numbers to it. AT, and then, I don't know, 562. And you send it to the Bluetooth device. Starting with, who is it? I don't know, I was speaking to somebody this week about.
It was a long time ago, but I was mentioning you, Qualcomm has these boards called CSR.
Yeah.
And it's Internet of Things.
Okay, how many of you remember, so lots of boards have this, okay? How many of you remember having to connect to the internet with like a modem on the phone? And it has that weird sound, it connects and goes, and all that, scratchy noise and stuff. Okay, internally, what's going on is these little symbols. AT something, it's a standard. It's a communication standard protocol, okay? And basically the UART inside of the Bluetooth module understands it. And you send it little commands like this from your Freedom board, and it'll convert it into a Bluetooth signal and allow signals to be sent back and forth to your phone. And all you have to do is a string of characters to be created within your Freedom board, and you send it out the UART, and Bob's your uncle, you're done. You just have to hook it up right. And if things aren't working quite right, you take your bus pirate, you hook it up with the little pins that are on here, the little hooks, and you can use your PC to decode the signals to make sure that you're running at the right baud rate, with the right parity, with the right error checking, okay? And you can verify things. Was there a question? Yes?
So the TX line, the RX line, are they pins on the thing, or is it the micro USB?
So what happens is you got this. So here's the KL board. There's the pi. TX, which is transmit, is the so you take transmit on one side, it goes to receive on the other side. Transmit on the other side goes to receive on the previous side. That's how you connect them up. Yes?
They're technically like satellites, right?
They're technically like which?
Like mini satellites, basically, to communicate.
Yeah, I guess you can think of it as satellites, yeah. Yeah, that's a good way of looking at it, yes.
So on a serial device, like on a mouse or something?
Yes.
Like the mouse wouldn't have a clock in it.
So would like a USB mouse? The answer is typically a USB mouse actually does have a clock in it. So the USB protocol, if I remember my protocol right, has 4 wires on it. Okay, ground and +5, and then it's called differential signaling. It's 2 signal wires that can either be receive or transmit at the same time, and it's the difference in voltage between the 2 wires that's understood. There's no separate clock. So you've actually typically got a microcontroller on board of the mouse that's responsible for doing the processing of the button pressing and tracking either the ball or the motion from the optical sensor or whatever else is going on. So there's typically a microcontroller on board. Yeah, so it does have a crystal and well, it has at least a clock on it, wherever that clock comes from. Yeah. So it's asynchronous.
But it has a clock on it.
It has both devices, the mouse and the PC, will have a clock on it, separate clocks. They talk to each other.
I thought you said if they both have clocks, then it's synchronous, and if one doesn't, then it's...
No. So if both have clocks, typically, but not always, typically they will be running asynchronously. Especially if they're using something like USB or a UART or RS-232 to talk to each other. Yeah. Okay? All right. Okay, so typically when you're looking at serial communication, you have multiple bits. There'll sometimes be a bit that announces the beginning of a signal, and then often there'll also be a bit that is responsible for saying, I'm done. Now, when we talk about serial communication, we often see this kind of, that kind of thing. These sort of diagonal pulses that go up and down. It means typically that the signal can be either high or low. If I do something like that. And the diagonal part of it means there can be some skew to it. It doesn't quite transition at sort of 90 degrees. So what we're saying right here is the signals are arbitrary. They can sometimes be high, they can sometimes be low. Depends, but we don't want to specify exactly which one it is because the different characters will be transmitted at different times and in different order. But often there will be some way of messaging that the packet of information starts. And the other thing to remember a lot of the time is that on a serial communication bus, the default position is a high voltage. So often when you connect 2 devices together and they haven't started speaking to each other, but they're just connected, you'll often have a high voltage connection between the 2 so that it's possible for whichever device it is to understand that it is connected to something else. It's not talking, but it's connected. Okay? So you have a start bit, and that's configurable. You have a stop bit, and then in the middle, you've got data bits. And the data could be something like 8 bits that represent the letter A, or the number 2, or a period, or a hyphen, or something along those lines. Typically think of each one of the sort of the data bits as being a key on the keyboard. That's typically what we're talking about when we're transmitting information as characters between one device and another. The other thing that's important to know is there's something called a parity bit. That parity bit is there for error checking because your signal can degrade for all sorts of reasons between the master and the slave or the slave and the master or the two devices that are talking to each other. And so what this parity bit means is that, and you have to agree to this particular standard, you either have no parity, so no error checking, you have even parity or odd parity. And what it means is that you are going to add all the high bits together, and if it's even parity, that bit will be set to make sure that the total addition is even, an even number. If it's odd parity, then all of those numbers, all those bits add up together, all the ones add up together to create an odd number. It is a simple error checking method. It's like the simplest one you can get. Yes?
Why do you have two pairs?
In this case, right here, there's only one parity bit. P.
Oh, so that, oh, okay, I thought that was.
Yeah, no, that's okay. So the parity bit, and then there's a stop bit right beside it. Okay, so when you use a terminal program, like CoolTerm or RealTerm, okay, so how many of you are Mac people? Okay, if you're a Mac person, CoolTerm, because you're cool, okay, is an awesome little program. If you're a Windows person, how many of you are Windows people? Okay, then you want RealTerm, because you use real computers. No, I'm a Mac person too. Okay, how many of you are Linux people? I have no idea. There are other programs for you, okay? But basically, if you want something free and something usable and something that's been around for many years in order to have a solid way of debugging your serial communication, CoolTerm for Mac, RealTerm for Windows. Okay, those are the two pieces of software you want to go to, and they're free, open source in some cases, but at least they're free. Okay, so we talked about error parity bits. There are other ways, more complicated ways of checking to see that the signal has degraded, but the parity bit is the standard thing that you will encounter. So often you'll see something like the communication is going to run at 115 kilobaud. It has even parity bits, one stop bit, no start bit. Okay, that's enough for you to know what the agreement is between the two devices. Okay, so when you get that Bluetooth module that you want to use, it'll often say something like, this Bluetooth module will speak on its UART at 9600 baud, one even parity bit, one stop bit, and 8-bit data. Okay, that's a typical configuration that you know, and you use that to configure CoolTerm or RealTerm or that client that is talking to it. Okay? All right. Now, I am a big advocate of debugging hardware and software, okay? Tools to allow you to understand better what's going on. Because how many of you got really frustrated with your project because you weren't sure? Yeah, I share your pain, okay? No, I do, I really do, okay? Like, I get it. I get what it's like to have this foreign piece of hardware that you really don't understand what's going on, and you're trying to get the registers to do something, or you're programming up the registers to do something, and the signal is supposed to come out, and you get nothing. Or you get something, and you have no idea what it is. Okay, like, I totally get that. There are tools on the market that are relatively inexpensive for you to help you understand what's going on. When you're dealing with serial devices, there are a couple of really good tools. The Bus Pirate is the most, it's kind of a little hard to use, but at $50, it is the cheapest of all of the serial decoding devices you can get that is like PC and Mac and Linux compatible. They'll work on all three, okay? That's one option for you. The problem with the Bus Pirate is that the interface is purely text, and the data that comes through is basically just text. So if you're more of a visual person, like you like oscilloscopes and things like that, it's not for you. But if you're on a budget and you can deal with the headache of learning how to use a text-based interface system, then the Bus Pirate's fabulous. If you want something a little bit, not high-end, but something more visual, then companies like Selig sell for about $150 this PC compatible logic analyzer, which is effectively what the Bus Pirate is. Okay, but it's more refined. It's a commercial product, and it allows you to see the signals that are generated, like I'm going to show you on the oscilloscope right here, and it allows for decoding. Now, does anybody have like $2,000 burning in their pocket right now? Okay, if you did, you could get an oscilloscope, a really decent, even for about $1,000, a decent Agilent or Keysight oscilloscope. And I know it sounds crazy, but on eBay you can get them for cheaper. Okay, you can get an oscilloscope, and if ever you're in the market for a second-hand used scope, and there are lots of good ones out there, HP, Agilent, Keysight, Rigol. So this is a Rigol right here, super cheap, $500 cheap. Okay, it's an oscilloscope. They're not like 50 bucks. If you're going to get one and you want one that can do the decoding for you, make sure that it has a serial interface or serial decoding protocol in it for RS-232, SPI, I2C, and they exist.
In all seriousness.
All seriousness.
Literally just looking at this on Amazon right now. Would this be something that you might consider purchasing if you had just graduated, just got a job, suddenly have money, and okay.
If you're going to be, okay, no, all seriousness.
Yeah, like
If you want to go, if you,
love throughout your career as an engineer.
how many of you would like to be electronics consultants, or start your own company to make stuff? Okay, then honestly, if you're going to do any electronics at all, on your bench, you should have, to begin with, a low-end scope. A Rigol like this, or a low-end Keysight, less than $1,000. Okay, brand new. 500 bucks used. And that is sufficient for you to get started. You don't want to start an electronics business without one. Okay? And with it, you can see what the bit patterns are and you can decode it manually. But then there are companies that make these logic analyzers for 150 bucks that plug into your PC that'll do that automatically for you. You can equip yourself to do this sort of thing when you have a little bit of money. Okay? I didn't own a scope like this when I was a student. Okay? My brother did, but that's the sort of guy he was. Okay? Like he was all kitted out. I didn't. I went to school and I borrowed it. Okay? But if you're going to start your own company, you're going to do that sort of thing, it's a decent piece of equipment to have. Okay? All right. So sidetracked right there. All right. Anyway, 150 bucks, you get a good system. Okay. When you use when you use a serial interface, you can either poll it or you can interrupt it. Today we're going to do an example using polling, but just like you can do interrupt-driven receiving and transmitting, you can do that. You can do that basically on any microcontroller that's out there. And so if you're going to get started, start off with polling-based systems because ISRs introduce a whole lot of like black magic to what you're doing. But if you need good response, low latency, etc., then you want to go to interrupt-based systems. They're the better way of doing it, but always start with polling. Okay. Either way you go, this is basically how it works. You've got some main program, and in the program, you will have a function, send a string. And by a string, we mean characters, like a char, but a bunch of chars in C. A, B, C, period, hyphen, numbers, etc. Okay? The ASCII, basically it's ASCII letters and numbers. And you have a function that sends a string. And what that does is it will put a series of letters and numbers and whatever into a buffer. That buffer will be the buffer of the SPI device or the UART, and it will take care of converting those letters and numbers into electrical signals. Okay, so the buffer goes into the serial interface, and the serial interface is a semi-autonomous piece of hardware inside that will deal with the intricacies of SPI, UART, etc., CAN bus, etc., things like that. Okay, whether it's interrupt-driven or polling-driven. On the KL43, this is what you got. You have, let's see, what we're going to do today, we're going to deal with the UART or the low-powered UART down here. It's pins D0 and D1. D0 is receive and D1 is transmit. You have, let's see, there's an I2S system over here, which is like I squared C. I've never used it. Over here, you have I squared C, and then you have SPI. So you have multiple interfaces that are available on the digital pins. So you can talk to I squared C devices, sensors, etc., SPI devices, etc., or UARTs. And the UART would be something that you'd use to talk to Raspberry Pi, for instance. Yeah, Nisha.
Is there also I2C something to help you out in the data sheet? Because I've looked at their examples for I2C in MCU Expresso.
Yeah.
But it's way too complicated. Like they're using too many functions, too many definitions.
So SPI and I squared C, they're complicated. And so my recommendation is right now, don't bother. UART is the simplest, most straightforward of the serial protocols that I would recommend at this stage, like this semester, that you worry about. Next year, in a different course, in a different project, then you can tackle the I squared C or the SPI interface. But for this course, don't bother. It'll be too complicated. The examples are too complicated. Yeah. Okay. All right. No? All right. So with the UART and the other serial interfaces, the way you start them up is the same way you start up all the other peripherals. You look at the SCGC registers. In this case, it'll be SCGC 4 and 5. So if you want to start up the SPI module, or the I squared C, or UART 2, or even the USB. So not the one used to debug, but the one that you would use to simulate a mouse or something. That's started up with SCGC 4. If you want to start up a low power UART 0 or 1, or if you want to start up the Flex IO system, that's an SCGC 5. Today, the example we're going to do is going to be with low power UART 0 because the example that's given in MCU Expresso is actually really easy. It's not trivial, but it's the easiest of all the examples. Sort of like, when I started with the timers, I started with that system tick because it was dead simple to get started. Same deal with LP, low power UART 0. It's the first one you want to deal with. Okay? So, UARTs, asynchronous. Basically, it means that we have an optional start bit. We've got data bits. Typically, there's 8 data bits to represent a letter or a number in ASCII. Then there's the error checking parity bit, and then there is a stop bit to tell the system that we are done with this particular pack of information. And you will notice if you hook it up to a scope that the transmit line is held high, and high means 3.3 volts on the UART. If you're dealing with another serial protocol like RS-232, the voltage level will actually be much higher. Okay, we'll skip this for the receiver because we're not going to do receiving today. We said the number of data bits, the order has to be specified, there has to be a discussion about stop bit and stop bit, or start and stop bits, and you always have to be acknowledging what kind of frequency you're dealing with. And by frequency, we're typically talking about the baud rate. Roughly the bits per second that are being transmitted. Okay, on the KL43, there's the low power UART 0 and 1. We will deal with UART 0. And then there's a higher power UART 2 that we're not going to deal with. So there are basically 3 asynchronous serial transmitters. Okay. And we'll skip this. Okay, here's this basic SimSys code. Okay. Now, in order to deal with the UART, you're dealing with D0 and D1, those 2 pins. D1 is the transmit or TX, and receive is the RX or D0 pin. Now, Let's imagine you've forgotten everything that you heard in this class and you have to look at it from scratch. Okay? First thing you do is you take a look at that diagram from the Embed website. You say, here are my pins. Those are the pins I need. And it tells you it's PTA 2 and PTA 1. Next thing you do. So this is step number 1. Always start with step number 1. Easy little diagram to look at. Next thing you do is you go to the schematic. Step number 2. And you see here that D0 and D1 are available right there, and they attach to connector J1. So now you verify that on your board you have those 2 pins available, because it would be really unfortunate if you wrote up all your software only to find out, and then you're trying to debug something and you realize you've been debugging the wrong pins. That is the worst. Spending 6 hours debugging the wrong pins and saying, why aren't I getting any voltage on these pins? It's because it was the pin right next to it. Okay, that's like a terrible feeling. The next thing you need to do is you do, what's that keyword that you want to look for in the data sheet? Alt-0. You do a search for Alt-0. So glad that's being retained. Alt-0, you hit Control-F twice. You get to this table. Inside of the table, you are looking for PTA 1 and PTA 2, which happen to be low power UART receive and low power UART transmit, and you know that it's going to be the Alt-2 multiplexing setting. Again, don't get this wrong, otherwise you'll never get the internal connection that you need. Okay, make sure that you actually set this properly. So those are the 2 things to remember right there. Next up is the code. So there is, I forgot to shrink this a little bit. Actually, give me a sec. Keep. There, that's better. So, there we go. Okay. So I didn't write the code myself. All I did was use the demo code, because I'm assuming that if you're going to start doing this as well, you're just going to start from the demo code, or you'll integrate the demo code into your own code. The demo code is the low power UART example, and in it there is an init function, and it's available, I believe, in pinmux.c. And what it shows you is that SCGC5 needs to be initialized, that there is the muxing that's going on right there as well. And then there's the option register for connecting up the specific type of clocking mechanism, not the on-off switch, but the frequency that needs to be used to drive this thing. Okay, that's what goes on initially. And so if you wanted to write your own code, you basically take the steps that are right here, but they should be familiar to you at this point. You turn on SCGC 5 or 6 or 4, that turns on the device, then you set up your mux, and then you set up the clock that's used to drive the synchronicity, basically. Yes?
What about for instance, my digital sensor? It has 3, which is 5 volts to ground, and SDA. Where should I put this SDA?
If you have an SDA line, so just so everyone's know what we're talking, SDA. Typically what this means is that you have an I2C, I squared C, serial interface. That's typically what it means, and that means that you, if we go back a couple of slides, it'll be the top pins in orange right there. There's your SDA right there. SDA and SDL, SCL, SCL. Yeah. So you have an I squared C. Now the problem is that you're running at 5 volts, and so you may require a level shifter to go from 5 volts to 3 volts. Maybe. I can't remember if the KL43 is 5 volt tolerant. So in some cases it doesn't speak 5 volts, but it can listen to 5 volts and not like flame out. Yeah. Can it?
Ultrasonic, yes.
Okay, there you go. Excellent. I've been too chicken to actually try. So I have all of you. All right, so you set up the clock, you set up the mux. It's the same step as ADC, GPIO, it doesn't matter. It's always the same thing, right? Over and over again. And if you decide you're going to write that test on Tuesday, if you decide you want to write it, then you'll have the data sheet available for you. And you just go through the same steps. Same thing each time. Okay? And just so you know, in terms of how that's going to get graded, it's not an all or nothing thing. If you have a partially working solution, then you will get a partial mark on that particular demonstration. Okay, so it's not all or nothing. All right, so after that, basically in the LP UART polling example, the next thing to point out is that you want to have arrays that can store character strings. And the character strings are stored, in this case you can see, they're stored as unsigned 8-bit integers. Because that's what they are. Characters are unsigned 8-bit numbers. They're just read as ASCII. They use the ASCII table as a lookup table, basically. Okay, so it's an array in memory, and in this case, in the example, they just wrote a sentence, and the UART will take each one of those characters and send it out one character at a time through. How does it do it? Basically, you have to configure up the UART for a particular baud rate. In this case, it's going to be 115,000 baud or 115 kilobaud. It will run at, let's see, parity mode right here, disabled, so no error checking. There will be no error checking bit. After that, there is one stop bit. So, and there's no, I don't believe there's a start bit. So it basically means there's going to be 8 bits of data plus 0 bits of parity plus 1 bit of stop, which means that the packet of information is going to be 9 bits long. Okay, and so if you're having to debug this, you're going to want to hook it up to the scope, and you're going to want to check to see if you actually see 9 bits. In terms of how you actually send this information, there's in the default code, in the example code, there's a reading function and a writing function. I'm only using the writing function because I've only hooked up one line on the scope right here, and I don't have another device for it to talk to. And inside that writing function, it basically has a while loop that goes through that structure, that array, and sends out the data one at a time until it's done. That's all it does. It just pumps the buffer for the system. Okay. Now, how many of you have that $2,000 for the super good scope? None of you. Okay, but you might have access to the oscilloscope for debugging. You might not have the bus pirate, but you have access to the scopes in the lab. Okay. How do you set up the scope in order to look at the pulses of information? Okay, so that's what we're going to do now. So anyway, does anybody have any questions about that? No? Okay, so I've put the program on the board. And so what I did is I hooked it up earlier, just when I got to class, and I plugged it in. I took my oscilloscope right here. I connected the ground line to ground, because you need that voltage reference. You need to have that. And the other line right here is to D1. That's all I've connected up. Does that make sense to everybody? So the transmit line I've got hooked up to the scope as one channel right there. And then what you can see right there is the signal that got sent out. All those letters you saw in the C code, they're represented right there as bits. And if I take, what else? The vertical scale. That's each one of the bits. So you see the little on the leftmost one, this little thin one, that's 1 bit. 1 bit, and then it goes up, then it goes down, then it goes up again, then it goes down. So let's see, it goes up, looks like it goes up twice, then down twice, then up twice, then down once, and then up maybe 4 times. Then it goes down once, and it's up 3 times, and it goes down. Those are the bits that represent the characters. And you basically look at each 9 of those. You actually have to look at the individual 9 there. Time it out, so you check how much time each one takes at the baud rate that we're dealing with, 115 kilobaud, or 115,000 bits per second. So you have to sort of divide it up on your scope. And you can actually decode what the letters and numbers in ASCII are using the ASCII table. Can it be a real pain? Yeah, but you can do it. Okay. Now, how would you set up your scope to capture this? Because if all you're doing is you just let the scope run by itself, the little burst of information will appear on the screen and then disappear again. Appear on the screen and disappear. And you won't be able to capture it in order to widen it out and decode it. Using a trigger. So Simon was saying using an edge trigger. And that sort of works, kind of, sometimes. There's another, so I tried it to see if it would work on the Rigel scope right here, and it didn't work. Okay? But triggering is important. So what you need to do is you take your trigger line, that's the trigger right there, and you want to set it to about, I don't know, it's a 3 volt signal, so like 2 volts. So you want it to trigger around there. You want to set it to trigger on a pulse. Okay? And the other thing to point out is that you want it, if at all possible, to trigger on a down pulse. Because your signal is always starting at top and then pulses down. So you want to be looking for that down pulse. So when you set this up on a scope, you want to capture on the down pulse, and then it can actually capture it. So if I go like this, I'm going to hit the reset button, and it captures it. I'm going to change the time scale, like that. I'm going to reset. So now there's nothing in memory. It's not visualizing anything. I hit the button right here, and it captures it. And then I can expand it on the time scale like that. Okay? So that's how, using somebody else's scope without anything really complicated, you can see whether or not the signal that you're hoping to see actually shows up. So if you want to do a basic test to make sure that your system is sending out a signal, this is how you do it. You go and capture almost an edge trigger. You're looking for a pulse trigger, triggering at a level of half, roughly, of what your maximum voltage is going to be, and then your scope will capture that event, that sort of asynchronous, arbitrary event. Okay, does anybody have any questions? No? You all ready to do this on the exam next week?
No.
It's not going to be on the test. It's not going to be on the test.
Can we go back to the code? Maybe review the code?
Yeah, absolutely. But honestly, next year during Eng 4000, in whatever group you are very likely to encounter team members that will want some of these higher end devices like GPS or Bluetooth or whatever. And the UART is the single most capable way of making it happen. Okay? So it's something to keep in mind for next year. Okay. So the code, yes. So, Chris, it was your question, yeah?
Yeah, I don't really have a question. I just want to see it.
Sure. And the slides are posted. And this is the code that actually appears within MCU Expresso. So you can grab this and use it.